In the beginning there is silence, a vast, unyielding silence that stretches across the cosmos where the universe holds its breath. The night sky unfurls like a velvet tapestry, pierced by countless stars, each a pinprick of light, a whispered promise of worlds unseen. They shimmer in the dark, their glow a testament to eons of creation, a celestial choir singing in wavelengths no human ear can hear. Yet among these quiet luminaries there are giants, colossal radiant titans that burn with a ferocity that defies reason, their light a roar across the void. These are not mere stars. These are the behemoths of the heavens, the hypergiants. Stars, so vast, so luminous, they shine with the brilliance of a billion suns. Picture a single point in the infinite dark, a solitary ember blazing with the intensity of entire galaxies. Its light does not merely illuminate, it commands. It is a torch flung into the abyss, a flame so fierce it threatens to consume itself in its own splendor. These stars, known to astronomers as hypergiants, are the universe's most extravagant spectacles. They are rare, fleeting, and catastrophic, their very existence a paradox, a dance of creation and destruction played out on a stage older than time. Their radiance is not just a phenomenon, it is a question, a mystery woven into the fabric of the cosmos. What are these titans? How can a single star burn with such unimaginable power? And what secrets do they whisper about the life and death of the universe itself? To gaze upon a hypergiant is to peer into the heart of a cosmic furnace. These stars, scattered sparsely across the Milky Way and beyond, are not content to merely exist. They dominate. A hypergiant like VY Canis Majoris, one of the largest known stars, sprawls across a diameter that could engulf the orbit of Saturn if placed at the center of our solar system. Its surface roils with storms of plasma, each eruption a cataclysm that could swallow worlds. Yet its size is only part of its enigma. Its luminosity, hundreds of thousands, sometimes millions, of times brighter than our sun, defies comprehension. If our sun is a candle flickering in the cosmic wind, a hypergiant is a supernova frozen in time, a star that burns so fiercely it seems to challenge the laws of physics. But this brilliance comes at a cost. Hypergiants are not eternal. They are born in violence, forged in the dense cores of collapsing nebulae where gravity crushes gas and dust into furnaces of nuclear fire. Their lives are brief, measured not in billions of years like our sun, but in mere millions, a fleeting moment in the cosmic chronicle. Their immense mass fuels a runaway fusion process where hydrogen and helium are transmuted into heavier elements at a staggering pace. This is no gentle alchemy. It is a frenzy, a star consuming itself in a desperate bid to outshine the heavens. And in that consumption lies their doom, for hypergiants are unstable, teetering on the edge of collapse, their own gravity a relentless adversary waiting to claim them. The suspense of their existence is palpable. Each hypergiant is a ticking clock, its core a battleground where forces of unimaginable scale wage war. Will it explode in a supernova, scattering its essence across the cosmos to seed new stars and planets? Or will it collapse into a black hole, a silent monument to its former glory? Astronomers, peering through telescopes like the Hubble and the James Webb, have only begun to unravel these questions. Data from NASA and studies published on ArXiv reveal that hypergiants are not merely outliers. They are key to understanding stellar evolution. Their rapid lives and violent deaths forge the heavy elements, carbon, oxygen, iron, that form the building blocks of planets, of life itself. Yet the mystery deepens. Why do some stars grow to such monstrous proportions while others remain modest? What conditions in the early universe allowed these giants to form? And what do their fleeting lives tell us about the ultimate fate of the cosmos? To study a hypergiant is to touch the edge of creation, to glimpse a universe that is both eternal and ephemeral. These stars are not just beacons of light, they are beacons of meaning, their fury a reminder of the delicate balance that sustains existence. As their light travels across billions of miles to reach our eyes, it carries with it a story of birth, of brilliance, and of an end that shapes the beginning of all things. The cosmos has always whispered its secrets, but only in the quiet of observation do they begin to take shape. In the early years of the 20th century, the night sky was a canvas of mysteries, its stars mere points of light to the unaided eye, each a riddle wrapped in radiance. Astronomers armed with rudimentary telescopes and insatiable curiosity peered into the heavens, cataloging the celestial fires that burned across the void. Among these they stumbled upon anomalies, stars that shone with a brilliance that defied reason, outshining entire clusters as if mocking the very laws of stellar existence. These were the first whispers of hypergiants, the titans of the cosmos, whose discovery would reshape humanity's understanding of the universe's grandeur and fragility. Long before the term hypergiant entered the lexicon, the heavens offered a spectacle that demanded attention. In the 1840s, a star in the constellation Carina, known as Eta Carinae, erupted in what history would call the Great Outburst. For a fleeting moment, this distant beacon blazed so fiercely that it rivaled the brightest stars in the night sky, visible to sailors and stargazers across the southern hemisphere. Its light, a furious cry across 7,500 light-years, pierced the dark with a luminance that seemed to belong to no single star but to a cosmic inferno. Observers of the time, wielding telescopes of glass and brass, could scarcely comprehend what they saw. Was this a nova, a star in its death throes, or something else entirely? A celestial giant whose power dwarfed all known measures. Eta Carinae's outburst was no mere flare. It was a declaration, a signal that the universe harbored stars of unimaginable scale, their lives as brief as they were brilliant. The mystery of these luminous giants deepened as the 20th century dawned. Astronomers, poring over photographic plates and spectral data, began to notice stars that refused to fit the orderly classifications of their peers. These were not the familiar dwarfs or giants of stellar theory, but outliers, radiant enigmas that burned with the intensity of thousands, sometimes millions of suns. Their light, captured in grainy images, seemed to pulse with a restless energy, as if each star were a heart beating against the confines of its own existence. Early theories faltered. Could a single star truly outshine a cluster? Could such a behemoth sustain itself, or was it destined to collapse under its own ambition? The answers lay beyond the reach of early instruments, but the questions lingered, etched into the margins of star catalogs like unanswered prayers. The true scale of these cosmic titans began to emerge with the advent of modern astronomy. In the 1980s, the Hubble Space Telescope turned its unblinking eye toward the heavens, piercing the veil of distance and dust. Among its targets was the Tarantula Nebula, a star-forming cauldron 170,000 light-years away in the Large Magellanic Cloud. There, nestled within a cluster of blazing young stars, astronomers found R136A1, a hypergiant so massive, so luminous it redefined the boundaries of possibility. This star, with a mass estimated at over 200 times that of our Sun, shone with a brilliance equivalent to nearly 9 million suns. Its discovery was not a triumph of intent, but a revelation born of anomaly. Scientists had not set out to find such extremes. R136A1 emerged from the data, a cosmic leviathan demanding to be understood. The European Southern Observatory's Very Large Telescope, perched atop the arid peaks of Chile's Atacama Desert, added clarity to the enigma. By dissecting the light of hypergiants like R136A1, astronomers measured their mass, temperature, and luminosity with unprecedented precision. These stars, they found, were not merely large but prodigious, their surfaces roiling with temperatures exceeding 40,000 Kelvin, their atmospheres sculpted by winds so fierce they could strip a planet bare. Yet their discovery was not a moment of conquest, but of humility. Each observation revealed how little was known about these stellar giants. Their spectra, parsed through prisms and computers, told tales of rapid fusion, of cores where hydrogen burned into helium at a pace that promised a swift and violent end. These were not stars that lingered. They were stars that raged. The journey to understand hypergiants was fraught with challenges. Early astronomers, like those who marveled at Eta Carinae's outburst, relied on visual estimates and crude photometry, their tools limited by the technology of their era. By the mid-20th century, spectroscopy had begun to unlock the chemical secrets of stars, revealing the presence of heavy elements forged in their cores. But hypergiants defied easy analysis. Their light, distorted by vast distances and interstellar dust, required telescopes of extraordinary power to resolve. The Hubble, with its mirror polished to near perfection, offered glimpses of their true nature, while the Very Large Telescope's adaptive optics countered the blurring of Earth's atmosphere. Together, these instruments painted a portrait of stars born in the densest regions of galaxies, where gravity and chaos conspired to create monsters. Yet the discovery of hypergiants was not merely a matter of technology. It was a shift in perspective. Astronomers had long viewed stars as stable, predictable entities, their lives governed by orderly processes of birth, evolution, and death. Hypergiants shattered this paradigm. They were anomalies, outliers that challenged the very models of stellar physics. Their existence suggested that the universe was not a place of uniformity, but of extremes, where the boundaries of possibility were stretched to breaking. Eta Carinae, with its twin lobes of gas and dust sculpted by its 19th century outburst, became a case study in instability. Its mass, once estimated at over 100 solar masses, hinted at a star teetering on the edge of collapse. Its core a battleground where gravity and radiation waged a relentless war. The discovery phase was not a single moment, but a slow unveiling, a dialogue between humanity and the cosmos. Each new observation of Eta Carinae's homunculus nebula, of R136A1's searing brilliance, added a verse to the poem of hypergiants. These stars, though rare, were not mere curiosities. They were key to understanding the universe's past and future. Their rapid lives and explosive deaths forged the heavy elements that seeded galaxies, shaping the raw materials of planets and life. Carbon, oxygen, iron, the building blocks of existence, were born in the hearts of stars like these, scattered across the cosmos in cataclysms that echoed for millennia. But the discovery of hypergiants raised as many questions as it answered. Why did some stars grow to such monstrous proportions while others remained modest? What conditions in the early universe allowed these giants to form? And how did their fleeting lives influence the evolution of galaxies? The data, drawn from NASA's archives and peer-reviewed studies on Archive, offered clues but no certainties. Hypergiants, it seemed, were not just stars but storytellers, their light a narrative of creation and destruction. To study them was to trace the arc of the universe itself, from its fiery beginnings to its distant, unknowable end. The discovery phase was an awakening, a moment when the universe revealed a truth it had guarded for eons, that among its countless stars were giants whose brilliance could not be ignored. Eta Carinae, R136a1, and their kin were not sought but found, emerging from the shadows of stellar catalogs to challenge humanity's understanding. Their light, traveling across vast distances, carried a message, a reminder that the cosmos is a place of wonder and terror, where beauty and catastrophe are two sides of the same coin. As astronomers turned their telescopes skyward, they did not merely observe, they listened, and in the radiance of hypergiants, they heard the universe speak. In the grand theater of the cosmos, where stars play out their lives across eons, a discovery emerged that shook the foundations of stellar science. Hypergiants, those colossal beacons burning with the fury of billions of suns, did not merely dazzle the eye. They defied the very principles that astronomers held as sacrosanct. These stars, radiant and reckless, stood as cosmic heretics, challenging the laws that governed the heavens. Their existence was a revelation, a jolt that forced scientists to confront a universe far wilder, far more precarious than they had dared imagine. To understand hypergiants was to peer into a crucible where creation and destruction danced in perilous balance, their brilliance a testament to a universe unafraid to break its own rules. The shock of hypergiants lay not only in their radiance, but in the audacity of their existence. Stars, as astronomers long understood, were bound by a delicate equilibrium. At their cores, the crushing force of gravity waged war with the outward push of nuclear fire, a balance that sustained them for billions of years. But hypergiants laughed at such restraint. Their luminosity pressed against a cosmic boundary, a threshold where the radiation pouring from their cores threatened to tear them asunder. This limit, named after the astronomer who first described it, marked the edge of stability, a point where a star's own light could no longer be contained, where its brilliance became a force of self-destruction. Hypergiants flirted with this edge, their surfaces roiling with a ferocity that seemed to mock the very notion of equilibrium. Their mass was equally staggering. For centuries, astronomers believed that stars could not grow beyond a certain size, that the forces of nature imposed a cap on their ambition. A star too massive, they reasoned, would collapse under its own weight or shed its outer layers in a desperate bid for stability. Yet hypergiants shattered this assumption. Some bore masses exceeding 150, even 200 times that of our Sun, their cores dense with the raw material of creation. These were not stars but titans, their immense gravity a furnace that burned through fuel at a prodigious rate. To gaze upon such a star was to witness a cosmic paradox, a behemoth that should not exist, yet blazed with a defiance that illuminated the heavens. The brevity of their lives added to the astonishment. while our Sun, a modest star, will endure. For some 10 billion years, hypergiants are cosmic lightning strikes, brilliant, fleeting, and catastrophic. Their immense mass fuels a relentless fusion, transforming hydrogen into helium, and helium into heavier elements at a pace that defies comprehension. In mere millions of years, a blink in the cosmic chronicle, they exhaust their cores, racing toward an inevitable end. This frenzied existence captivated astronomers, for it suggested a universe where beauty was born of instability, where the brightest lights cast the shortest shadows. Each hypergiant was a star in a hurry, its life a fleeting burst of glory before the darkness claimed it. The instability of these giants was perhaps their most unsettling trait. Hypergiants were not content to burn steadily. They erupted, their surfaces convulsed by outbursts that released more light in moments than entire galaxies over centuries. Consider Eta Carinae, whose great outburst in the 1840s briefly outshone every star in the sky. Such events were not mere tantrums but cataclysms, expelling shells of gas and dust that formed nebulae visible across light years. These eruptions hinted at a star on the brink, its core a battleground where gravity and radiation clashed in a struggle that could end in collapse or explosion. To study a hypergiant was to watch a star teeter on the edge of oblivion, its every pulse a reminder of its fragility. The very idea of a star radiating with the brilliance of a billion suns once seemed like the stuff of myth. Astronomers, steeped in the orderly mathematics of stellar evolution, could scarcely believe that such entities existed. Yet observations gathered through the unblinking lenses of telescopes, like the Hubble and the Very Large Telescope, confirmed their reality. These instruments revealed stars like R136A1, a hypergiant in the Tarantula Nebula, whose light rivaled that of millions of suns combined. Its spectrum, parsed through prisms and analyzed by computers, told a story of a star so massive, so luminous, that it seemed to bend the rules of physics. The data, drawn from NASA's archives and peer-reviewed studies, painted a picture of a universe where extremes were not anomalies, but inevitabilities. The shock of hypergiants lay in their defiance of expectation. Stellar models, built on decades of observation, predicted that stars followed predictable paths, their lives dictated by mass and composition. But hypergiants were rebels. Their existence suggested that the universe was not a place of tidy order but of wild possibility, where stars could grow to monstrous proportions and burn with a fury that challenged comprehension. This realization forced astronomers to rethink their key assumptions. If stars could reach such extremes, what else might the cosmos conceal? Could there be other phenomena yet unseen that pushed the boundaries even further? The implications of hypergiants extended beyond their own existence. Their rapid lives and violent deaths were crucibles for creation, forging the heavy elements that seeded the universe. Carbon, oxygen, iron, the building blocks of planets of life, were born in the hearts of stars like these, scattered across the cosmos in explosions that echoed for millennia. To study a hypergiant was to trace the origins of existence itself, to see in its radiance the raw materials of worlds. Yet their instability raised troubling questions. Could such stars, in their death throes, trigger chain reactions that altered the evolution of galaxies? Could their outbursts reshape the cosmic landscape, leaving behind voids or nebulae that influence the birth of new stars? The scientific shock of hypergiants was not just a matter of scale, but of philosophy. These stars forced astronomers to confront the limits of their understanding, to question the very nature of the universe. Were hypergiants aberrations, or were they harbingers of a deeper truth? Their existence suggested that the cosmos was a place of extremes, where the boundaries of possibility were not fixed, but fluid. Each observation, each spectrum was a step toward unraveling this mystery, yet the answers remained elusive. The light of hypergiants, traveling across vast distances, carried with it a challenge: to see the universe not as a finished work, but as a story still being written. As astronomers peered deeper into the cosmos, they found themselves drawn into the orbit of these radiant giants. Each hypergiant was a puzzle, its brilliance a question mark, etched in fire. Their discovery was not a triumph, but a humbling, a reminder that the universe was vast and unknowable, its secrets guarded by stars that burned too brightly to endure. To contemplate a hypergiant was to stand at the edge of creation, to feel the weight of a universe that was both beautiful and terrifying. Their light, though fleeting, illuminated a truth: that the cosmos was a place of paradox, where the brightest stars cast the darkest shadows, and where the line between existence and oblivion was as thin as a single breath. The universe, in its vast silence, guards its secrets with a fierce indifference. Yet humanity, with its insatiable hunger for truth, has crafted tools to pry open the cosmos's hidden chambers. In the quest to understand hypergiants, those celestial titans that burn with the fury of billions of suns, astronomers turn to instruments of exquisite precision, each a key to unlocking the mysteries of these radiant giants. Through spectroscopy, X-ray observations, and infrared probes, they pierce the veils of dust and distance, revealing the chaotic lives of stars that seem to defy the very laws of existence. Each discovery deepened the enigma, painting a portrait of stars so luminous, so unstable that their brilliance was a prelude to their own destruction. To investigate a hypergiant was to walk the edge of a cosmic precipice where beauty and catastrophe were one. Spectroscopy, the art of dissecting starlight, became the first torch in this celestial exploration. By splaying a star's light into its constituent colors, astronomers could read its secrets as one might read an ancient manuscript. The spectrum of a hypergiant revealed a story of searing temperatures, often tens of thousands of degrees hotter than the surface of our sun, where atoms danced in frenzied agitation. These spectra were not mere rainbows, but chronicles, etched with the signatures of elements, hydrogen, helium, and traces of heavier metals, forged in the star's core. Each line in the spectrum was a whisper from the heart of the giant, telling of nuclear fires that burned with relentless intensity. Yet these same spectra hinted at turmoil, their patterns distorted by the star's violent convulsions, as if the light itself trembled under the weight of its own creation. Beyond visible light, astronomers turned to the invisible. X-ray telescopes, like NASA's Chandra, peered into the high-energy chaos surrounding hypergiants, where shockwaves from their explosive outbursts collided with the interstellar medium. These X-rays revealed a universe in upheaval, where the star's own ferocity sculpted its surroundings. Infrared observations, meanwhile, cut through the cloaks of dust that often shrouded these giants, unveiling their hidden brilliance. Instruments, like the Spitzer Space Telescope, captured the glow of material ejected by hypergiants, glowing faintly in the infrared as it drifted into the void. Together, these tools painted a picture of stars not merely shining but raging, their light a battle cry against the darkness that sought to contain them. The Hubble Space Telescope and the European Southern Observatory's Very Large Telescope offered a visual poetry to this investigation. Their images, crisp and haunting, captured the dynamic lives of hypergiants in vivid detail. They revealed stellar winds, torrents of charged particles streaming from the star's surface at speeds that could cross the Earth in seconds. These winds were not gentle breezes, but tempests, stripping away layers of the star's outer envelope and casting them into space. In some cases, entire solar masses were ejected in a single outburst, forming glowing nebulae that lingered like ghosts of the star's former self. To observe these winds was to witness a star unraveling, its brilliance a double-edged sword that both defined and doomed it. No hypergiant told this story more vividly than Eta Carinae, a star whose scars were as visible as its radiance. In the 1840s, its great outburst had lit up the night sky, a flare so brilliant it rivaled the brightest stars. The aftermath of that event, captured in exquisite detail by Hubble, was the Homunculus Nebula, a pair of glowing lobes of gas and dust expanding outward like the wings of a cosmic butterfly. This nebula was no mere ornament, it was a testament to a star that had nearly torn itself apart. The material within, equivalent to several suns, had been hurled into space during the outburst, a violent act that left Eta Carinae diminished, yet still luminous. To study the homunculus was to read the biography of a star caught in the act of self-destruction. It scars a map of its turbulent past. Patterns began to emerge from these observations, each a thread in the tapestry of hypergiant behavior. Instability was their hallmark. Unlike their smaller kin, hypergiants did not burn with steady grace. They pulsed, their brightness waxing and waning in cycles that hinted at chaos within. Some, like Eta Carinae, erupted in spectacular outbursts, shedding vast swaths of their mass in moments of cosmic frenzy. Others, like RE 136A1 in the Tarantula Nebula, unleashed relentless stellar winds, streams of material so powerful they carved cavities in the surrounding gas clouds. These winds were not mere breezes but hurricanes, carrying away the star's substance and hastening its demise. Each cycle, each eruption was a reminder that hypergiants were not built to endure. Their lifespans, astronomers found, were as fleeting as they were brilliant. While our sun will shine for billions of years, hypergiants race through their lives in mere millions, a cosmic heartbeat, swift and fleeting. Their immense mass fueled a runaway fusion process, where hydrogen and helium were transmuted into heavier elements at a staggering pace. This was no gentle alchemy but a conflagration, a star consuming itself in a desperate bid to outshine the heavens. The cost of such brilliance was clear. Hypergiants were unsustainable, their radiance a flame that burned too fiercely to last. Each observation deepened this sense of impermanence, as if the universe had crafted these giants to shine briefly, then fade into legend. The deeper investigation revealed a universe of extremes, where the brightest stars were also the most fragile. Data from NASA's telescopes and peer-reviewed studies on R-Corsiv confirmed that hypergiants lived on the edge of a cosmic precipice. Their proximity to the Eddington limit, the point where radiation pressure threatened to tear them apart, meant that every outburst, every pulse, was a gamble with oblivion. Some astronomers speculated that these stars were relics of the early universe, born in dense regions where gravity could forge such monsters. Others wondered if their instability held clues to the formation of black holes or the explosive supernovae that scattered heavy elements across the cosmos. Each theory was a step toward understanding, yet each left the mystery intact. To study a hypergiant was to confront the paradox of creation. These stars, with their prodigious mass and luminosity, were the universe's most extravagant artisans, forging the elements that would one day form planets, oceans, and life. Yet their very brilliance ensured their destruction, their lives, a fleeting burst of glory before the inevitable collapse. The homunculus nebula, with its glowing lobes, was a monument to this duality, a star that had survived its own near death, yet bore the scars of its recklessness. Other hypergiants, like those in the Tarantula Nebula, told similar tales, their winds and outbursts shaping the cosmos even as they hastened their own end. The investigation was not without its challenges. The light of hypergiants traveling across vast distances was often dimmed by interstellar dust or distorted by the turbulence of their own atmospheres. Telescopes had to be pushed to their limits, their mirrors and sensors tuned to capture the faintest signals. Spectroscopy required meticulous calibration, as the slightest error could obscure the truth. Yet with each new observation, the portrait of hypergiants grew clearer. Their instability, their winds, their fleeting lives, all pointed to a universe where beauty was born of chaos, where the brightest lights cast the shortest shadows. As astronomers delved deeper, they found themselves not merely observing, but listening. The light of hypergiants, captured in spectra and images, was a language of its own, speaking of creation, destruction, and the delicate balance between. Each star was a story, its radiance a chapter in the cosmic epic. To investigate a hypergiant was to trace the arc of the universe itself, from the fiery forges of its birth to the silent voids of its end. These stars, unsustainable and magnificent, were not just anomalies but revelations. Their brilliance a reminder that the cosmos was a place of wonder and peril, where the line between existence and oblivion was as fragile as a single breath. The cosmos is a crucible of contradictions, where the brightest stars burn with a ferocity that both illuminates and annihilates. Hypergiants, those radiant titans whose light rivals billions of suns, stand as the universe's most audacious creations, yet their very existence deepens the enigma of their origin and fate. How could such monstrous stars form when the forces of gravity and radiation conspire to halt their growth? What cosmic alchemy allows them to defy the laws that govern lesser stars? And what consequences do their violent lives unleash upon the galaxies they inhabit? Each question, like a star's light piercing the void, only reveals a deeper darkness, a mystery that grows more profound with every discovery. Hypergiants are not merely stars, they are harbingers of catastrophe, their brilliance a prelude to cosmic upheaval. The formation of hypergiants is a riddle wrapped in the fabric of the universe itself. Stars are born in the dense hearts of nebulae, where clouds of gas and dust collapse under gravity's relentless pull, igniting nuclear fires that sustain them for eons. But hypergiants, with their colossal masses, sometimes exceeding 200 times that of our Sun, should not exist. The radiation pouring from their embryonic cores should scatter the surrounding material, starving the star before it can grow to such prodigious size. Yet there they stand, blazing defiantly in regions like the Tarantula Nebula, their presence a challenge to the orderly mathematics of stellar birth. Astronomers, poring over data from NASA's telescopes and peer-reviewed studies, grapple with this paradox, their minds alight with questions that echo across light years. One tantalizing hypothesis suggests that hypergiants are not born but forged, products of stellar mergers where two or more stars collide in a cosmic crucible. In the crowded nurseries of star-forming regions, where young stars swirl in chaotic orbits, such collisions are not mere possibilities but inevitabilities. Picture two massive stars, each a furnace of nuclear fire, spiraling toward one another, in a dance of gravity and destiny. Their union is no gentle embrace, but a cataclysm, a fusion of light and matter that births a monster. The resulting hypergiant, swollen with the combined mass of its progenitors, burns with a fury that outshines its peers, its radiance a testament to the violence of its creation. This theory, supported by simulations on Archive, offers a glimpse into a universe where creation is born of destruction, where the brightest stars are sculpted by chaos. Yet the mystery of hypergiants extends beyond their birth to the havoc they wreak upon their surroundings. These stars are not solitary beacons but cosmic architects, their violent lives reshaping the galaxies they inhabit. Their stellar winds, torrents of charged particles streaming at unimaginable speeds, carve cavities in the interstellar medium, sweeping away the raw material of future stars. In regions like the Large Magellanic Cloud, where hypergiants like R136A1 reign, these winds sculpt nebulae into fantastical shapes, their tendrils glowing with the light of creation and ruin. But it is their instability that truly sets them apart. Hypergiants pulse with erratic rhythms, their surfaces racked by convulsions that hurl vast swaths of material into space. These outbursts, like those of Eta Carinae in the 19th century, release energy that can briefly outshine entire galaxies, their light a warning of the chaos to come. The destiny of a hypergiant is not endurance, but annihilation. Their immense mass and ferocious fusion shorten their lives to mere millions of years, a fleeting moment in the cosmic chronicle. As their cores exhaust their fuel, they face a fate that is both spectacular and terrifying. Some erupt in supernovae, explosions that scatter their essence across the cosmos, seeding the universe with the heavy elements that form planets and life. Others, pushed to the extremes of mass, may unleash hypernovae, cataclysms so powerful they dwarf ordinary supernovae, their shock waves rippling through galactic arms. But the most massive hypergiants face an even stranger end: pair instability, supernovae. In these apocalyptic events, the star's core becomes so hot that photons themselves trigger a runaway collapse, obliterating the star entirely and leaving no remnant behind. The universe, in a single moment, erases its own creation, as if the star's brilliance was too great to be contained. Speculation deepens the mystery further. Some astronomers propose that the most massive hypergiants may bypass explosions altogether, collapsing directly into black holes of intermediate mass, elusive objects that bridge the gap between stellar mass black holes and the supermassive giants at the hearts of galaxies. Such a collapse would be a silent apocalypse, the star's light snuffed out as gravity claims its final victory. These intermediate mass black holes, though yet to be definitively observed, could hold the key to understanding how supermassive black holes form, their origins tied to the violent deaths of hypergiants. The idea is tantalizing, a thread connecting the smallest scales of stellar evolution to the grandest structures in the cosmos, yet it remains shrouded in uncertainty, a hypothesis that dances on the edge of possibility. The instability of hypergiants is not a flaw but their essence, their destiny, written in the fires of their creation. Each pulse, each outburst, is a step toward their inevitable end, a reminder that the universe is a place of impermanence. Their light, captured by telescopes like the James Webb and the Very Large Telescope, tells a story of stars that burn, too brightly to endure. Eta Carinae, with its homunculus nebula, stands as a monument to this truth, a star that survived its own near destruction, yet bears the scars of its recklessness. Others, like R136A1, continue to rage, their winds and eruptions shaping the cosmos even as they hasten their own demise. To study a hypergiant is to witness a star in rebellion, its brilliance a defiance of the darkness that awaits. The deeper astronomers probe, the more profound the mystery becomes. How do hypergiants form in a universe that seems designed to prevent them? Could their births in the dense cores of ancient galaxies hint at conditions long vanished, relics of a younger, more chaotic cosmos? And what of their deaths? Do they seed the universe with life, or do they carve voids that stifle creation? The data, drawn from NASA's archives and the latest studies, offers glimpses but no certainties. Each observation is a brushstroke on an unfinished canvas, revealing a universe where order and chaos coexist in delicate balance. Hypergiants, with their fleeting lives and catastrophic ends, are not mere anomalies but storytellers, their light a narrative of creation and destruction. To contemplate a hypergiant is to stand at the threshold of the unknown, to feel the weight of a universe that is both magnificent and merciless. Their existence challenges the boundaries of possibility, forcing astronomers to rethink the laws that govern the stars. Their instability, their violence, their brilliance all speak to a cosmos that thrives on paradox, where the brightest lights cast the darkest shadows. As their light travels across billions of miles, it carries a message that the universe is not a place of permanence but of transformation, where every star, no matter how grand, is but a fleeting note in an eternal symphony. Hypergiants, in Dail, their radiant defiance, remind us that even in their destruction, they shape the destiny of the cosmos, their legacy etched in the elements that form the worlds yet to come. In the vast cathedral of the cosmos, where stars are both architects and epitaphs, hypergiants stand as enigmatic monuments, their radiance a challenge to the laws that bind the universe. These celestial titans, burning with the fury of billions of suns, defy explanation, their existence a riddle etched in light across the void. How do such monstrous stars form when the forces of nature seem arrayed against them? What cosmic machinery sustains their brilliance only to doom them to a fleeting existence? And could they be echoes of a primordial era when the universe itself was young and wild? Astronomers, armed with telescopes and theories, venture into this uncharted territory, their minds alight with speculations that weave science and wonder into a tapestry of cosmic possibility. Each hypothesis is a thread, pulling at the mystery of hypergiants, yet revealing a universe more complex, more profound than any could have imagined. The birth of a hypergiant is a paradox that haunts stellar theory. Stars form in the dense hearts of nebulae, where clouds of gas and dust collapse under gravity's relentless embrace, igniting nuclear fires that burn for eons. But hypergiants, with masses far beyond what models deem possible, should not exist. The radiation pouring from their embryonic cores should scatter the surrounding material, starving the star before it can grow to such prodigious size. Yet, In regions like the Tarantula Nebula, these giants blaze defiantly, their presence a rebuke to the orderly mathematics of stellar birth. One theory, drawn from simulations and observations, suggests a process of relentless accretion, a cosmic feast where gas clouds pour into the forming star at a rate that defies the push of its own light. Picture a nascent star, a voracious infant, drawing in streams of gas through turbulent channels, its gravity overpowering the radiation that seeks to tear it apart. This delicate balance, sustained in the chaotic nurseries of galaxies, allows a star to swell beyond all reason, its core a furnace fueled by an unrelenting hunger. But accretion alone cannot fully explain the existence of hypergiants. Another hypothesis, bold and dramatic, proposes that these titans are not born but forged, products of stellar mergers, where two or more stars collide in a cosmic crucible. In the crowded cores of star-forming regions, where young stars swirl, in chaotic orbits, such collisions are not mere possibilities but inevitabilities. Imagine two massive stars, each a beacon of nuclear fire, spiraling toward one another in a dance of gravity and destiny. Their union is a cataclysm, a fusion of light and matter that births a monster. The resulting hypergiant, swollen with the combined mass of its progenitors, burns with a fury that outshines its peers, its radiance a testament to the violence of its creation. Studies on Archive, bolstered by computational models, lend credence to this idea, suggesting that mergers in dense stellar clusters could sculpt the giants that dominate the heavens. Yet this theory raises new questions. How frequent are such collisions, and what conditions allow them to produce stars of such extreme mass? The internal dynamics of hypergiants add another layer to the mystery. Rotation and magnetic fields, invisible forces that shape a star's life, may play a pivotal role in their stability or lack thereof. A rapidly spinning star, its surface, a whirl of plasma, could resist the crushing pull of gravity, allowing it to grow larger than its slower kin. Magnetic fields, threading through the star's interior like cosmic veins, might channel its energy, stabilizing its structure against the chaos of its own radiance. Yet these same forces can destabilize, twisting the star's core into knots of instability that trigger violent outbursts. Observations of stars like Eta Carinae, with its erratic pulses and massive ejections, hint at such dynamics, their spectra revealing the signatures of magnetic turmoil. But the balance is precarious, a tightrope walk between creation and collapse, and astronomers remain uncertain whether these forces are saviors or saboteurs in the life of a hypergiant. The most extreme fates of hypergiants push speculation to the edge of the unknown. In their cores, where temperatures soar to unimaginable heights, a phenomenon known as pair instability may seal their doom. Here, photons, particles of light, become so energetic that they transform into pairs of electrons and their antimatter counterparts, destabilizing the star's core. This process, theorized through complex models, triggers a runaway collapse, culminating in an explosion so powerful it obliterates the star entirely, leaving no remnant behind. Such pair instability supernovae are rare, reserved for the most massive hypergiants, yet their implications are profound. The energy released in these cataclysms could outshine entire galaxies, scattering heavy elements across the cosmos to seed new stars and planets. The thought is both awe-inspiring and unsettling. A single star, in its death throes, could reshape the destiny of a galaxy. But not all hypergiants meet such explosive ends. Some, astronomers speculate, may collapse directly into black holes. of intermediate mass, elusive objects that bridge the gap between the stellar mass black holes formed by ordinary supernovae and the supermassive giants at the hearts of galaxies. This silent collapse, where a star's light is snuffed out by gravity's final embrace, would leave no visible trace, only a gravitational shadow rippling through the cosmos. Such black holes, though yet to be definitively observed, could hold the key to understanding the origins of their supermassive kin, their formation tied to the violent deaths of hypergiants. The idea is tantalizing, a thread connecting the smallest scales of stellar evolution to the grandest structures in the universe. Yet it remains a hypothesis, a whisper in the data that begs for confirmation. The mystery of hypergiants reaches beyond their birth and death to their place in the cosmic saga. Could these stars be echoes of a primordial universe, relics of an era when the first stars, known as population 3 stars, burned with unimaginable intensity? These ancient giants, born in the aftermath of the Big Bang, were forged in a cosmos devoid of heavy elements, their cores fueled by pure hydrogen and helium. Models suggest they were far larger and brighter than even the hypergiants of today. Their lives brief but transformative. Their explosive deaths scattered the first heavy elements across the universe, seeding the galaxies we now inhabit. Hypergiants, with their prodigious mass and luminosity, may be their distant descendants, carrying the legacy of those primordial titans. To study a hypergiant is to glimpse the dawn of creation, to see in its light the faint glow of a universe newly born. Theories and speculations swirl around hypergiants like the stellar winds that sculpt their nebulae. Each hypothesis, grounded in data from NASA's telescopes and peer-reviewed studies, is a step toward understanding, yet each deepens the enigma. How do these stars form in a universe that seems designed to prevent them? What role do their violent lives play in the evolution of galaxies? And could their deaths, whether explosive or silent, hold the key to the cosmos's deepest secrets? The light of hypergiants, captured by instruments like the James Webb Space Telescope, tells a story of creation and destruction, of stars that burn too brightly to endure. Their instability, their radiance, their fleeting lives, all speak to a universe where chaos and order are intertwined, where the brightest lights cast the darkest shadows. To contemplate a hypergiant is to stand at the crossroads of science and wonder, to feel the weight of a cosmos that is both eternal and ephemeral. Their existence challenges the boundaries of possibility, forcing astronomers to rethink the laws that govern the stars. Each theory, each speculation, is a brushstroke on an unfinished canvas, revealing a universe that thrives on paradox. Hypergiants, with their monstrous mass and catastrophic fates, are not just stars, but storytellers. Their light a narrative of a cosmos in constant transformation. As their radiance travels across billions of miles, it carries a message that the universe is a place of impermanence, where even the mightiest stars are but fleeting notes in an eternal symphony, their legacy etched in the elements that will one day form the worlds yet to come. In the silent expanse of the cosmos, where hypergiants blaze with the fury of billions of suns, humanity's quest to unravel their mysteries unfolds with tools of exquisite precision. These celestial titans, radiant and ephemeral, challenge the boundaries of understanding. Their light a cipher that beckons astronomers to peer deeper into the universe's heart. Observatories, both earthbound and spaceborne, stand as sentinels, capturing the fleeting brilliance of these stars. From the piercing gaze of telescopes to the subtle tremors of gravitational waves, each instrument is a thread in the tapestry of discovery, weaving a narrative of stars that burn too brightly to endure. Yet, with every observation, the enigma of hypergiants deepens, their lives a dance of creation and destruction that demands ever more ingenious methods to decode. To study them is to chase a cosmic phantom, a pursuit that reveals the universe's grandeur and its impermanence. The Hubble Space Telescope, a beacon of human ingenuity orbiting above the Earth's turbulent atmosphere, has long stood at the forefront of this quest. For decades it has trained its unblinking eye on Eta Carinae, a hypergiant whose violent outbursts have etched scars across the heavens. Hubble's images of the homunculus nebula, twin lobes of gas and dust, hurled from the star during its great outburst in the 1840s, are haunting in their clarity, revealing a star caught in the act of self-destruction. Each observation captures the nebula's expansion, a slow-motion explosion that speaks of a star teetering on the edge of oblivion. The telescope's spectroscopy, dissecting the star's light into its constituent colors, reveals a chemical saga of hydrogen, helium, and heavier elements forged in its core. These observations, drawn from NASA's archives, paint a portrait of a star that pulses with instability, its radiance a fleeting cry against the darkness. On Earth, the Very Large Telescope in Chile's Atacama Desert stands as a titan among observatories, its mirrors polished to capture the faintest whispers of light, using adaptive optics, systems that bend and flex to counter the distortion of the atmosphere. It has peered into the heart of the Tarantula Nebula, where R136A1 burns with a brilliance that defies comprehension. This star, among the most massive known, radiates with the intensity of millions of suns, its surface a maelstrom of plasma sculpted by ferocious winds. The telescope's precise measurements of its mass and luminosity, gleaned from the subtle shifts in its light, reveal a star that pushes the boundaries of possibility. Each spectrum is a story, telling of temperatures so searing they could melt worlds, and of winds that strip away the star's substance, casting it into the void like a cosmic offering. Beyond visible light, the universe speaks in wavelengths, unseen. X-ray telescopes like NASA's Chandra and the European Space Agency's XMM Newton probe the high-energy chaos surrounding hypergiants. These instruments capture the glow of shock waves, where stellar winds collide with the interstellar medium, igniting bursts of X-ray light. The data reveals a universe in turmoil, where hypergiants sculpt their surroundings with relentless force. For stars like Eta Carinae, these observations uncover the hidden violence of their outbursts, their winds crashing against clouds of gas and dust to produce fleeting flares of energy. Each X-ray pulse is a testament to the star's power, a reminder that its brilliance is not merely light, but a force that reshapes the cosmos. The James Webb Space Telescope, humanity's newest eye on the heavens, pierces the veils of dust that shroud the births of hypergiants. Its infrared vision, tuned to the faint glow of warm gas, reveals the cradles where these giants are born, dense nebulae where gravity and chaos conspire to forge monsters. In regions like the Carina Nebula, Webb captures the embryonic stages of massive stars, their light obscured by the very clouds that feed them. These observations, rich with detail, offer clues to the processes that allow a star to grow beyond reason, its core igniting in a blaze that will one day outshine its peers. The telescope's images are not mere snapshots but windows into creation, showing a universe where the seeds of catastrophe are sown in the act of birth. The future promises even greater revelations. In the high deserts of Chile, the extremely large telescope is rising, its massive mirror designed to dwarf all that came before. With a diameter spanning dozens of meters, it will capture light with unprecedented clarity, probing the atmospheres of hypergiants to reveal their chemical secrets. Its adaptive optics, more advanced than any yet built, will sharpen the view of stars like R136A1, allowing astronomers to track their pulses and eruptions with exquisite precision. Meanwhile, the Roman Space Telescope, poised to launch into orbit, will map the rare populations of hypergiants across distant galaxies. Its wide-field surveys will uncover these elusive giants, their light a beacon in the cosmic sea, offering a census of stars that burn at the edge of possibility. Beyond light, the universe speaks in ripples of space-time. Gravitational wave detectors, like those operated by LIGO and its global counterparts, listen for the tremors of cosmic collisions, events that may give birth to hypergiants, stellar mergers, where two massive stars fuse in a cataclysm of light and gravity. Could be the forge where these titans are crafted. The faint ripples of such events, traveling across billions of miles, carry the signatures of their violence. Detecting these waves would offer a new lens on hypergiant formation, confirming theories that paint them as the products of cosmic chaos. Each signal, captured by delicate instruments, is a whisper from the universe's past, a clue to the origins of its brightest stars. Supercomputer simulations, the alchemists of modern astronomy, push the boundaries of understanding further. These digital crucibles recreate the lives of hypergiants, modeling the physics of their birth, their furious burning, and their catastrophic ends. Simulations, informed by data from observatories and published on platforms like Archive, test the limits of accretion, exploring how gas clouds can feed a star beyond theoretical constraints. They probe the dynamics of stellar mergers, recreating the collisions that birth monsters. And they delve into the pair instability process, where photons in a star's core trigger a collapse that obliterates it entirely. Each simulation is a hypothesis brought to life, a virtual star that burns and dies to reveal the secrets of its real counterparts. Yet with every tool, every observation, the mystery of hypergiants deepens. Their formation defies the laws that govern lesser stars. Their lives a fleeting burst of glory before an inevitable end. Are they relics of a primordial universe, echoes of the first stars that lit the cosmos? Do their deaths seed galaxies with the elements of life, or do they carve voids that stifle creation? The data, drawn from NASA's missions and peer-reviewed studies, offers glimpses but no certainties. Each image, each spectrum is a brushstroke on an unfinished canvas, revealing a universe where beauty and chaos are intertwined. To study a hypergiant is to chase a fleeting vision, a star that burns too brightly to endure. The tools of astronomy, telescopes, detectors, simulations, are humanity's attempt to capture this vision, to hold the light of a cosmic titan before it fades. Their radiance, their instability, their catastrophic fates, all speak to a universe that thrives on paradox, where the brightest lights cast the darkest shadows. As astronomers peer into the heavens, they do not merely observe, they listen, their instruments tuned to the symphony of creation and destruction. Hypergiants, with their fleeting lives and cosmic influence, remind us that the universe is a place of impermanence, where even the mightiest stars are but notes in an eternal melody, their legacy written in the elements that will one day form the worlds yet to come. In the vast tapestry of the cosmos, where light weaves threads across eons, a single star can burn with such ferocity that it outshines the collective glow of billions. These are not mere celestial lanterns dotting the night with timid flickers. They are titans, radiant behemoths whose brilliance defies comprehension. Their fire is a testament to the universe's audacity. Yet their story is not one of permanence, but of transience, a fleeting blaze that illuminates the dark before collapsing into silence. These stars, known to astronomers as hyperluminous giants or quasar progenitors, embody the paradox of existence. Their beauty lies in their fragility, their brilliance in their brevity. To stand beneath the light of such a star, if one could, would be to witness nature at its most reckless. These are not the steady suns that cradle worlds like Earth in their gentle warmth. They are cataclysms in slow motion, their cores churning with the fury of thermonuclear alchemy. Within their hearts, hydrogen fuses into helium, helium into carbon, and carbon into heavier elements still, iron, oxygen, silicon, each step a violent dance that releases torrents of energy. NASA's observations of such stars, captured through the piercing gaze of telescopes like Hubble and the James Webb, reveal their staggering power. A single hyperluminous star can emit energy equivalent to 1 billion suns, its light traveling for billions of years to reach us. A whisper from a time when the universe was younger, wilder, more untamed. But this radiance comes at a cost. Thy star's own hunger consumes it, its massive core, compressed by gravity's relentless grip, burns through its fuel with insatiable greed. Where a star like our Sun might endure for 10 billion years, these giants live for mere millions. A cosmic blink. Their lives are brief, yet in their deaths they gift the universe with the seeds of creation. When such a star exhausts its fuel, it does not fade quietly. It erupts in a supernova, a detonation so luminous it can outshine an entire galaxy for weeks. The explosion scatters the star's heavy elements, forged in its fiery core, across the void. Carbon, oxygen, gold, uranium. These are the ashes of such stars, strewn into the interstellar winds, destined to coalesce into planets, oceans, and even the fragile forms of life. This is the profound irony of the cosmos. Destruction begets creation. The violent death of a star seeds the raw materials of existence. Every atom in the human body, every molecule in the air we breathe, was once forged in the heart of a star like these. The iron in our blood, the calcium in our bones, the nitrogen in our cells, all were born in the crucible of stellar furnaces. As astronomers have traced through spectrometry and cosmic chemistry, detailed in studies from institutions like Caltech and published on platforms like Archive, the elements of life are the legacy of these ancient giants. Humanity, in its essence, is stardust, sculpted by the cataclysms of the deep past. To contemplate such a star is to confront the impermanence of all things. These celestial titans, burning with the power of 1 billion suns, are not eternal. Their light, though it seems to defy the darkness, will falter. Their brilliance, though it outshines galaxies, will dim. And yet, in their fleeting existence, they embody the universe's daring. They are not content to linger in quiet stability. They burn with reckless abandon, as if to proclaim their existence to the void. Their story mirrors our own, a brief flare of consciousness in the vastness of time, a momentary spark that seeks meaning before it fades. The cosmos, as revealed by observatories like the Atacama Large Millimeter Array, is littered with the remnants of such stars. Their deaths give rise to nebulae, vast clouds of gas and dust that shimmer with the glow of new possibilities. These nebulae, illuminated by the ultraviolet light of nearby stars, become nurseries for new suns, new worlds. The cycle is unending. From the ashes of one star, another is born. Yet, the hyperluminous giants stand apart. Their sheer power suggests they may have played a unique role in the universe's youth when galaxies were forming, and the cosmos was a cauldron of chaos and creation. Could these stars have been more common in the early universe? Observations from the James Webb Space Telescope, peering back to the epoch of ionization some 13 billion years ago, suggest that such luminous giants may have been the architects of the first galaxies. Their intense radiation could have ionized vast regions of hydrogen, clearing the cosmic fog and allowing light to travel freely. Their deaths, in turn, may have birthed the supermassive black holes that now anchor the centers of galaxies like our Milky Way. These black holes, some weighing billions of solar masses, are enigmas in their own right. Did they form from the collapse of single massive stars or through the merging of smaller remnants? The question lingers unanswered in the data streaming from deep space observatories. The mystery deepens when one considers the sheer scale of the universe. Are these hyperluminous stars common, hidden by the veils of dust and distance that shroud the cosmos? Infrared surveys, such as those conducted by the Spitzer Space Telescope, hint at their presence in far-off galaxies, their light redshifted by the expansion of space, yet their true abundance remains uncertain, obscured by the limits of our instruments and the vastness of the universe itself. Each new discovery, each new spectrum analyzed, adds a piece to the puzzle, but the whole remains tantalizingly out of reach. To reflect on these stars is to grapple with the nature of existence itself. They are not merely objects in the sky, but emblems of the universe's dual nature, its capacity for breathtaking beauty and unfathomable destruction. They remind us that creation is not a gentle process, but a violent one, born of fire and chaos. The supernova that ends a star's life is not an act of defiance against nature, but an expression of nature at its most daring, its most reckless, its most alive. These stars do not burn to endure. They burn to create, to scatter their essence across the cosmos, to weave the raw material of worlds yet to come. In their light, we see our own reflection. Humanity, too, is fleeting, a momentary flare in the grand arc of time. Like these stars, we strive to shine, to leave a mark, to create meaning in the face of impermanence. The elements in our bodies, forged in the hearts of ancient stars, tie us to the cosmos in ways both humbling and profound. We are not separate from the universe, but part of its unfolding story, a story written in light and fire, in birth and death. And so, the stars burn on, their light a beacon across the ages. They burn too brightly to last, yet in their fall, they give the universe the seeds of life. In their fragility lies their greatness, stars that dare to shine with the power of a billion suns. The cosmos watches, silent, as their light fades into the dark, leaving behind a legacy that endures in the rocks of planets, the breath of creatures, and the quiet wonder of those who gaze upward, seeking answers in the night.